Okay, so we have just two more things before the reception at the end of the day. We have Bill's talk coming up, and then we'll have a general panel discussion with the speakers and the audience. So let's go right into Bill Freeman on seeing faces and images.
Thank you. Can everyone hear me okay? Good. So this is a topic I love, and this collaboration has been really fun. It is with Mark Hamilton, Simon, grad student with me, Simon Stent, who's a psychophysicist at Toyota, Vasha Dutel, Jen Corbett, and Ruth Rosenholtz, who are all psychophysicists at CSAIL, and myself. And it started from a problem I kind of posed, and I always wanted to give it as a problem to my class in computer vision. And so I know that it's been 23 years since I've been thinking about this, and I just never did, but finally I was motivated to do it. And that's to ask them, how long would you have to look at the waves in the Charles River before it spelled out Highville or whatever? So here's Memorial Drive, MIT, there's the Charles River, here's the task. You sit there and look, and how long do you have to look before you see, Hi Pietro or whatever, spelled out in the waves? That's the task. And this is a sort of general case of seeing things in noise. And this is an age-old perceptual issue that people have noticed all the time. It's in Shakespeare, for goodness sakes. And so if we can turn up the volume here.
Speak with you and presently. Oh, do you see yonder cloud? It's almost in the shape of a camel.
It is indeed like a camel.
He thinks it's like a weasel.
It is backed like a weasel.
Oh, like a whale.
It is very like a whale.
So it's in Shakespeare. And then now I have to apologize to Andrew. There was a second motivation for doing this, in addition to addressing this 23-year-old problem that I've been interested in. And that is, I was preparing for giving a talk at this workshop celebrating a milestone birthday for Andrew Zisserman. And so because this is going to relate to a video I'm going to show you at the very end of the talk, I have to bring this up. I apologize. But so I wanted to find pareidolic Andrew. So I worked for 4 months on this talk to find pareidolic Andrew. And then why find pareidolic Andrew? Because he hates to be photographed. And if we're going to take more pictures of him, we better come up with some way, that doesn't require his cooperation. So here's, so here are my pictures of Andrew, and we just need some. So the goal then of that work was to find pareidolic Andrew. Okay, and I only tell you that because it's not going to be all about Andrew, but at the very end it becomes about Andrew again. So I want to explain why. Okay, so here's what the talk is going to be like. First of all, we gathered a data set, the sort of the knee-jerk response of any computer vision researcher for any computer vision task. So we gathered a pareidolic data set, 5,000 images of pareidolic, these faces that really shouldn't be there in the images. And so what do? First of all, we test whether state-of-the-art computer vision face recognition algorithms see faces in pareidolia. What do you think? Well, the answer is no, they don't. And then we train them on them, and using this labeled data set, we can train them so they do much better. Okay, but now then the question comes up, well, why do humans see pareidolic faces? They don't have a labeled training data set. Why do they see it? And we're going to propose an answer for why. And then the third line down, we'll take a little palette cleanser. We're just going to look at pareidolia in line processes, and I will at that time pose to you what I call the profile puzzle, which is a perceptual puzzler. I don't know the answer to it, but with this esteemed audience, I am sure that there will be 3 or 4 people who will definitively say they know the answer, and I bet they'll all be different. But I'm interested to hear what you think the answer is for what I'm going to call the profile puzzle. Then back to the main talk. We'll introduce 2 different mathematical models of pareidolia to address the questions, why does it come about? Why don't we always see pareidolia? How can we construct a random process which will make pareidolia most likely? And then we'll go back to Andrew again at the very end and show you this video about the lunar surface. Okay. So face pareidolia comes up everywhere. This is, a manufactured object which has pareidolia. This is the middle one there is the famous man in the mountain in New Hampshire, which is a sad story. It was a random process of weathering of this rocks generated a profile of a person there. And the entire, not the entire, but a lot of the New Hampshire economy was built around this, and it's on all the speed signs, all the state highway signs have that profile in it, and actually someone's job was to keep it from eroding, and anyway it fell down around 2003, and it's no longer there. But anyway, live and die by random processes. Okay, so some background on face pareidolia. It's just common. It used to be thought that it was some abnormality, but everyone shows it. They're there in adults and in infants. It's thought that there's a specialized network in the brain that responds to pareidolia. Strangely, pareidolic faces are most likely to be perceived as male. And it's a very fast process. It happens right away that you see pareidolia. And this kind of supports what we're going to propose as a reason for why humans see pareidolia. Other primates also experience pareidolia. Okay, so we gathered a data set of pareidolic images. And how did we do it? Well, our data set has 5,000 images. It's a subset of the 5 billion image data set LION. And we have human-drawn bounding boxes around every pareidolic entry. So I wasn't involved in the data collection, but they did it in a clever way. They would query with CLIP for images that said pareidolia, or faces in things, or accidental faces, or something looks like a face, and that gave them all these images to study. Then they had a human toss out the bad ones and label the remaining ones. We also tossed out any images of actual human faces or actual animal faces. And here are the statistics on, of course, we have the obligatory Antonio Torralba average of all the images in the data set. So the pareidolia images are on the left, and then an average of human faces is on the right there. And we collected this additional information, which we're not going to use in this talk, but the data set has them, and so they could be used for further studies. Was it easy to spot or hard to spot? Is the pareidolia by accident or by design? So that manufactured object that you saw, presumably that was by design. The man in the mountain was by accident. What is the emotion of the pareidolic face? Is it a person or a creature? What's the gender? And we confirmed that 80% of them are, neutral is 80%, but still there's of the ones that do seem to have a gender, they're mostly seem to be male. Of course, this is, we don't know why. And are they amusing or not? Okay, so now question number one is, do state-of-the-art computer vision face detectors see faces in these pareidolic images? So we picked one state-of-the-art algorithm called retinal face, and we picked, it's one of the best performers on this face in the wild data set called wider face, and the authors have two different versions of retina face for two different network architectures, one with MobileNet and one with ResNet 50, and we tried both of them on the data set, and they kind of failed right out of the box. 7.9% correct detection or 2.8% correct detection, depending on which architecture we used. There's a later step, which we'll use for some of the other things I'll tell you, where there's a fine tuning stage. And so as a control, we just applied the fine tuning on the human data set to make sure it doesn't break anything. But no, the story is the same, that they don't really detect pareidolia. If instead we fine tune the retina face on pareidolic images, so now this algorithm then has been trained both on human faces and on like 70% of the pareidolic images in our data set, then it can do a reasonable job of finding pareidolic faces, going from 10% detection to 34% or 27% detection.
Paradoxically, the older face detectors might actually be better. I mean, if you tried, say, Viola Jones or something like that, because in that era, it was all based on sort of a very blurred version of the face, and those might in fact actually do better on this task, because it's a question of defining what's a true positive or a false positive.
Okay, thank you. Yes?
I would suggest the other way around.
Student and teacher disagree.
I think the generative models, when used as classifiers, might actually do better, right? Because then you're not overtraining it on actual faces.
Okay. Okay, thank you. Okay, so now, at step one, we have a data set, and we show that at least the particular one state-of-the-art detector doesn't show pareidolia. If we can fine-tune it, then it does detect pareidolic faces. Why do humans see pareidolic faces? They obviously haven't trained with this labeled data set. Why do they see them? And here's a little conjecture, and that is that human faces all look, if you squint, very similar to each other, okay? But there's a lot more variability with animal faces than there are with human faces. So what if, and presumably for evolutionary reasons, humans are just rock solid quick at detecting animal faces as well as detecting human faces, because you want to detect the tiger in the leaves and so forth. So, so that's what we're going to explore next. And there has been previous work suggesting a link between human pareidolia and fast detection of predators. And I'm just I read over those papers, I can't really figure out whether when they say predator, they mean another human from the other tribe, or whether they mean a tiger. But anyway, it's, the pareidolia is a really fast thing, and then later the representation goes to include the objects that are composed of pareidolic image, but it's very, very quick. So we asked, well, what if we train these, to explain why humans have pareidolia, what if we take our face detection model and train it on animal images? How will that affect how the face detector works on pareidolic images? So we used this animal web, which is a large-scale hierarchical data set of annotated animal faces, and we fine-tuned the face detector on the animal faces. And what do you think happens? Yes, if it's learning to accommodate all these extra variabilities, you might imagine it's going to do better on pareidolic faces, and indeed it will. So first of all, the Taralba test. Here's the average images of the different data sets now. We got the average of the pareidolic, average human, average animal. And how does it do? It just does much better. It takes you, fine-tuning on the animal images takes you half the way to fine-tuning on the fully labeled pareidolic data set. So in other words, here's kind of out-of-the-box face detection on the pareidolic data set. It doesn't do very well. Here's if you really just train on labeled pareidolic images, and if you train on labeled animals, you get halfway there. And so this is one, conjectured explanation for why. I mean, there may be many reasons. I'm sure there are many reasons why humans experience pareidolia, but one could be that it's so important to recognize any kind of face that you see anywhere quickly that would motivate evolutionarily humans to be good at pareidolia. So here's a kind of visual description of what the table shows. So red is the ground truth labeling of the pareidolic faces. Blue, which you don't see very many, are out-of-the-box detection. If by a human face detector, it doesn't tend to see them. But if we fine-tune on animal features, on animal faces, then many of the times it sees the pareidolic face. And yet another slide supporting that. We tried a number of modifications to the fine-tunings on the state-of-the-art human face detector. Sobel operation, motion blur, Gaussian noise fog. These helped a little bit to detect pareidolic faces, but the one that really helped was animals, fine-tuning animals, and many things degraded performance, of course. Also, interestingly, conversely, if you have an animal detector and you fine-tune on pareidolic faces, you get a better animal detector, which is animal face detector. And you can see it just one more time if you look at a t-SNE plot of the retina net features with various fine tunings. So here's the retina net features, this two-dimensional squashing of the high-dimensional feature vector for something that detects humans, and then something that detects animals is in green, and detects pareidolic faces is in red. And the animals and the pareidolic faces, those features in this two-dimensional projection, they're all mingled together. And we couldn't resist, as a way of emphasizing again how important it is to be able to very quickly detect animals, point out that this really looks like a frog. Okay, fine. So now we're ready for the palette cleanser. So we have our data set, and we have a conjecture for why humans have developed pareidolia. By the way, another question I want to ask you is that a thing? I mean, how seriously should I take this possible reason for why humans have pareidolia, that we're used to looking at animals? Not at all? Great, thank you, perfect. Let's talk. Okay, excellent answer. Okay, and then now, okay, back to Andrew. I needed to come up with a way, some random process that would generate images of which I could search through and find one that looked like Andrew Zisserman. And what's the most efficient way to do it? I was thinking, well, a 2D process, you got this 2D thing, maybe a line process is going to be more efficient because, artists are so good at coming up with just, very small strokes of a line that evoke all sorts of things that they want to depict. And then also, if you go to the web and look on pareidolic images on the web, about half of them are profile pareidolic images. So, the Old Man Mountain, this one is called Sleeping Elephant. And this brings to the profile puzzle that I'd like your help with. They all seem to be profile views. You never see a configuration of rocks when everyone says, oh, there's a 3/4 view of a person's face there. Nobody says that. It's only profile or nothing. That's the puzzle. And so to kind of address this, I took a face renderer and traced out the different profiles of it from different face orientations, and that's shown here. And some of these just don't look very face-like. And so here's what they actually came from. So this is that one on the left that you may have thought was a profile face, this one. It's actually not really a profile face. It's kind of viewed from the top at a different angle. Here's one that is profile. This one's not profile, that one's not profile, and they don't really look like faces so much. So this is the profile puzzle. Why is it that we only see a face if it's a profile view of the contour? So, esteemed audience, do you have ideas? I knew you were going to say. Sorry, yes?
Signal is stronger there, right? I mean, if you look at the variation in curvature, and you try to think of the contrast, if you will, the signal is stronger in the side view than in a 3/4 view. So imagine that you have some detector which is trying to measure the orientations and change in orientations and build something on top of that. That signal has a maximal contrast in the side view.
Okay. Any other competing ideas? Yes.
I think you're using parts to generate pareidolia. Like when you see eye part, and you generate face. When you see like nose, then you generate face.
Okay, thanks. And I have a different proposal. I think maybe the side view is actually more stable, and the contour is going to be last for more rotational degrees than the other ones, which will be changing more quickly. But I don't know. Anyway, we can discuss later. Just wanted to bring that up. Okay, so back to Andrew. So I was sitting there looking for a reason, what can I do? And so I thought, okay, the spaghetti process. Let's use that to try to generate profiles of Andrew. And it's kind of slow. And then I thought, well, maybe I'll try to meet it both ways. Like I'll go on the perceptual side too. So I asked my artist friends. I showed them pictures of Andrew Zisserman. It's like, hey, can you draw with just a single stroke, something that might look like a piece of spaghetti, this picture. And we got all of these images. And I really love them. Unfortunately, they don't really look like Andrew per se, but I like them as images. And so and also I had I didn't explore it as fully as I should have, but I only had about 250 or so examples. But sorry, what? Counterexample. You found Andrew, or? No. Where's the three-quarter? Sorry, I see a face here. A full front.
It's face on.
No, I know. No, I understand that. I got it. There's pareidolia with both 2D processes and 1D processes. But if you constrain yourself to a line, why is it only profile view? Why not three-quarter view?
Okay, I didn't.
Yeah. Oh, okay. Sorry. Okay. Yeah. Got it. Thanks.
Nature.
No. No, I think there are plenty of front of view. Thank you. Okay. So, and I was about to give up, but then I thought, well, let's try to get some value out of all this spaghetti. So I made a pareidolic spaghetti alphabet from all these, and I could address the initial question that I started the talk with, which is I could sort of estimate from this how long it would take to spell out high bill in spaghetti. Okay, so I tossed out 219 pieces, but then I sort of cheated because I allowed myself to turn my head and everything, and so I estimated that to do it without turning your head, I'd have to throw in an extra 12 times for every one because there were 12 different angles I was rotating to and 2 reflections. So really, to get a single letter, I would have to toss it 5,256 times for any one letter. To get the 7 in a row for high bill, it would be this race of 7, or about 1 times 10 to the 26 tosses before I would see high bill in spaghetti. Anyway, just that, so we addressed that question. Okay, now we're back from the palate cleanser, back to the last part, mathematical models of pareidolia. So we want to know, how does it come about? What are the conditions that how do we tweak things to make pareidolia most likely or least likely? And so what I have then, we have 2 little mathematical models of pareidolia, and I'll explain them both to you. And they both predict the same testable effect. And then after this, we're going to go and test for that effect. But first, let me tell you the models. So to make a model of pareidolia, you need 2 things to model. You need to model the random surface that you're looking at. And you also need to model a detection process for seeing a face in that random surface. So first, let's do a Gaussian model. So Gaussian everything. Gaussian random process generating the texture, Gaussian detection process. Now you say, oh, what a terrible model. It's, we're so far beyond Gaussians now. Why strain yourself that way? But Gaussian models are just beautiful because they're generally tractable. You can find a closed form solution. And they're not far off. They give you the lay of the land. They tell you what the main issues are, and then you can go and refine them later. So let's start with the Gaussian model. So we'll assume that it's the way we generate the water waves or anything is by a Gaussian process. So we have some number of modes. So if you take this thing, let it run, and do PCA on it, you get this pattern of normal modes. The beauty of a Gaussian model is you get to consider the problem just one mode at a time, and they're all statistically independent of each other. So the way you generate this wave process is one by one, you go through and you draw from the Gaussian of a variance described by this particular normal mode, and you take that much of this thing, and then you go to the next one, draw from a Gaussian of the variance of this particular normal mode, add that much into the thing, do that for all of them, and you get an image. And then you get to do your detection process, again, one normal mode at a time. I won't bother forcing us all to memorize the notation, but it's all pretty simple. I'll show you on this graph. So for any one normal mode, you say, well, I know that my image of Andrew, pardon me again, but just so compelling to have the name. My image of Andrew has this coefficient for this mode. And so you want to know how big should the variance of my random process be to generate this. And then once you've generated a sample from that random process, you want to know, well, how probable is that found sample to be recognized as Andrew? In other words, what's the likelihood term? How far away are we from the true value of that sample for Andrew's face? And so this tells you to do the following. You This wide Gaussian, which is your random process, your water waves, or your rock formation, the variance of this mode this is a Gaussian of one variance, and then you say, well, given that I drew this value from that Gaussian, what's the probability that it was with a face I wanted to see? And so that's also a Gaussian. You can then you want to find the marginal probability, integrate over all possible values that you might have drawn to find the probability that you would have seen the Andrew coefficient in this normal mode. And again, the beauty is you can just do that analytically. And here's the closed form solution for finding the probability of your target face value and at that particular normal mode over a whole image is multiplied together for all normal modes are all independent. Great. Now you can see just from this one example, this effect that we're going to call peak pareidolia. Suppose you make the width of your Gaussian process too narrow, that it just can't ever get out to that sample that you need to generate the face you're looking for. Well, the probability of pareidolia is going to be really low. If this thing's really narrow, you're never going to get a sample that's way out here. Then you say, okay, well, I'll make it really wide. So if you make it really wide, then you will eventually get this sample, but you'll get so many other things too that the chance that you got that one sample you're looking for is also going to be low. And somewhere in the middle, you're going to get what we'll call peak pareidolia, where it's most likely. So here's another way of saying that. I guess I won't go through these, but these pictures on the bottom tell the story. Suppose you have a process with different numbers of normal modes. Suppose you have a very few normal modes here. Well, this is the best you can do to generate a face, and it's not much of a face. So even though it's pretty likely that every once in a while you'll get the random draw of these like 2 or 3 modes to get this image, the image doesn't look very much like a face, so the probability of pareidolia from this thing is very low. Conversely, if you take a lot of modes and you draw samples from them all, yeah, you can eventually get something that looks quite a bit like a face, but the odds of getting that are so low. And so it's in between there, we call peak pareidolia, where you'll see it. And again, the math just shows it to you. So let's look at a set of different random processes. So this is all independent Gaussian noise filtered to different amounts, so with different normal modes remaining. Here's like white television noise to those of you who are younger than 30 years old. It used to be that when you turned the TV on, you'd just get speckle. But it's like the beginning of the HBO, or now Max. Anyway, it looks like this. Okay. And then here's just very few modes. And then here's in between. And the model predicts that peak is going to be somewhere in here. If you look at these things, you'll be most likely to see a face. And if you look like these, you won't be likely to see one, although it could generate a beautiful one, but just so unlikely that it would. And similarly, you just can't make one here, so it's unlikely there also.
So the power, what are the power spectra? Are they this?
So right, it's not being displayed here. Actually, a few slides from now, I will show you the power spectra. But it was there's white noise, and then I filtered it with a Gaussian cutoff of wider and wider extent. So this one has only the center, a Gaussian width of spatial frequencies, and then it makes broader and broader and broader to generate these.
No, I was wondering whether you're fitting like natural image statistics.
Right. Yeah. Sorry. Yeah. So I forgot to say that. We're assuming that the face we're looking for has a 1/f power spectrum. Thank you. So the Gaussian model, the whole story is just all in the power spectrum. You have your target face you want to look for, and here for this plot, we're assuming it's got a 1/f power spectrum. And then you've got the random process, and it has its own power spectrum. And this, that formula I just showed you tells you how probable it'll be that you'll see an example of that template in these random noise images.
So Bill, you're not talking about the perception side, which was displayed in red in the previous figure, but it didn't explain how you decide how broad is the perception side.
Right. Yeah, right. That's right. There's two. Yes, there's different Gaussians in this Gaussian model. This is the kind of the likelihood term perception side, and no, I'm not. In general, for these things, I made it kind of as narrow as possible. Thank you. Okay. Yes. Yeah. Right. Okay. And then just for completeness, I want to show you a different toy model, which actually has the same peak pareidolia effect. let's not do a Gaussian model. Let's say something like what Pietro Perona did. Let's have kind of a feature detection model. Of course, many people have also done this. That you say the way you generate detection of a face is you have some set of features, some library of features, and you've got to detect this feature at this location or within some area of it, and you got to detect this feature over there within some area and so forth. And so converting into a model of pareidolia, we'll say that our random process has some Poisson probability of generating any one of these features. And then the way you make a face is that in zone 1, where for detection, you've got to have 1 occurrence of feature 1 and 0 occurrences of the other features. And then in zone 2, you've got to have 1 occurrence of feature 2 and 0 occurrences of the other, and so forth. And I won't bother doing the notation, but you might kind of guess what the notation is here. You can actually just run that through the Poisson, the counting statistics, to tell you as a function of your rate parameter what the probability is that the features will line up just right, so that you'll have just 1 example of this one over there, just 1 example of this one over there, 1 there, and 0 in the other places. And if you just plot that, you also get a peak. Now here the axes are different. Here this is the rate parameter for the Poisson process of detecting a feature. So, and then the vertical axis is probability that all the features line up, having 1 in each of the places you need to generate a face. So again, the story is, if your rate parameter is too low, you're just not going to see features anywhere. It's going to be like a blank wall, or maybe you'll just see 1 feature, and so you won't detect a face there. If it's too many, then it's just going to be garbage within your windows, and you won't detect a face there. And then in between, you'll have peak pareidolia. Okay, all right. So both of these come up with a testable prediction that if you order your random processes basically by complexity, you'll have a kind of low in the ends and high in the middle. And so let's test that. So this enters the psychophysics part of the talk. When do I stop? 5 minutes from now. Okay. Okay, 5-ish minutes. Fine. Thanks. So Vasha Dutel led this part, and she basically, showed people on a screen these random noise images and asked them, how many faces do you see? And what it looked like? Well, it looks like this. So again, these are the same filterings of Gaussian random noise, different random draws, of course. And now on the vertical scale, we're not plotting the Gaussian model's prediction. Instead, we're plotting the human reporting of how many times they see a face for these different random noise images. And so you can see the peak pareidolia structure there. And then we said, well, gee, let's test our algorithms. Do they exhibit peak pareidolia? And they do. So again, we tested them on these same random noise images, and really all the different flavors of the face detectors we tried also showed a peak around the middle of that continuum. Okay, so we're just left with Andrew now. Okay, so back to this 4-month-long preparation for this talk for Andrew. By about month 2, I was really getting, by the end of the second month, I was getting worried, and it wasn't working out. I couldn't find pareidolic Andrew. My family was beginning to mock me about this whole process. So here's a vacation video that my wife took from our vacation to Martha's Vineyard. Here's how she narrated the video.
Oh, look, there's Andrew. And there he is. There he is.
Okay, and then, I eat lunch with my daughter, and she said, oh, is that Andrew Zisserman? And so I was just getting worried about this. I needed to, sort of, and so I, as we all do, I went to my students for help. And Mark Hamilton helped me out of this. And I should say, it's that wonderful transition that happens where you propose a project to a student, and then 6 months later, it's their project, and they're first author and running everything. So that was the case here. Initially, though, it felt very much like Don Quixote, where Don Quixote is this guy who kind of sees these giants in the windmills, and Sancho Panza, the loyal sidekick, he knows that there aren't giants in the windmills, but he humors the old guy and helps him anyway. And so it's exactly the same here, that Mark knew that there were not images of Andrew Zisserman on the lunar surface, but he helped me look for them anyway, and I'm just very, very appreciative. So, okay, so step one. So we thought, okay, so, spaghetti, water, let's go for the lunar surface. And so step one is let's use our Gaussian model and see whether that's a good candidate. So again, with the Gaussian model, the whole story is what's the power spectrum of these things. And now finally, I'm showing you the power spectrum of those axes, plots on the horizontal axis that we had before. These are the power spectra of the different ones. And here's the power spectrum of this image from a lunar orbiter. It's not exactly the same as anyone, but it's roughly in between the power spectra of these two here. Where are they on the spectrum of peak pareidolia? Well, they're right at the peak. So for this viewing distance of this image, it's a good candidate for finding pareidolic images of faces, and of Andrew in particular. We use the Lunar Reconnaissance Orbital camera, which has a wide-angle global morphological map. So first, let's find the faces, and we found various faces, but nothing really jumped out. And then we said, okay, let's really we not it's a harder problem. We not only want to find a face, we want to find Andrew's face. So we used the contrastive loss. How close this was to the lunar surface, and then we divided by how close it was to all the other images in Celeb A, because we don't want it to look like any of them. We just wanted it to look like Andrew. And then we tried different representations for applying this loss. We used a FaceNet representation, Dino representation, and a pixel representation. And so these are all these candidates, and you can kind of look through and see if you find one that's a good candidate for Andrew. We felt we hit kind of bingo with that one there. Now, if you look there and look there, we think it's a pretty good likeness. And then by now, Mark Hamilton was just ready to make it be his project, and he just initiated and made this whole video all. I didn't ask him to do it; he just made it all on his own. So I want to share with you then a little video showing where Andrew is on the lunar surface. So now, before I play it, fortunately, it's on the back side of the moon. So he doesn't have to worry about being exposed to everyone. And it's right here, which is about a third of the way from Crater Mendel to Mare Orientale. Again, these are not features we're familiar with because it's on the unobserved side of the moon. And here's where it is. Let's see. Okay, so to summarize then, we introduced a database of pareidolic images. We asked the question, do current face detectors exhibit pareidolia? No. Why do humans see pareidolic faces? Well, if you train on animal faces, it gets you half the way toward training on actual pareidolic faces, and I look forward to hearing why that's just totally baloney. Thank you. As a break, we looked at line processes and addressed the question of how long does it take to see high bill. It took a long time. And I posed the profile puzzle to you. Then we had two different mathematical models of pareidolia, which gives us testable hypothesis that there should be a peak pareidolia, not too complex, not too simple. And indeed, that's borne out by our psychophysics tests and also by our computational tests. And then finally, we found out where Andrew really was on the moon. And thanks.
Okay, questions? Feel free to.
Yeah, okay.
I do.
So, well, sorry, just here.
So faces are special, and one could argue that maybe faces have an evolutionary pressure to be recognized. So how would you see differences if you picked some other natural thing that doesn't have that pressure? I don't know, like a maple leaf or something like that. Do you have any predictions of that?
So the mathematical models would work through just the same. They only care about the.
So they don't care. They don't see.
They don't
it.
care about the. They just take about the feature detection rate and about the power spectrum. The human psychophysics, well, I don't know how that'd be different. But I bet Justine could tell us.
It's a kind of evolutionary determinism. That is, it's an untestable hypothesis. I mean, it's a great hypothesis because there's no way of disproving it, which is why I abandoned it before starting.
Okay.
But I would add that it would be super interesting to do the psychophysics with babies to see whether there's a developmental curve, because that is testable and interesting.
Thank you.
So after a talk with so much poetry, it is difficult to ask a question which is very much prose, but I'll do so anyway. I mean, this issue of face detection, right? I mean, maybe we should think about at least this nitty-gritty of what criterion for success, because there's always, for any detector, there's a precision recall curve, ROC curve, whatever, right? Now, where you choose to be on that curve, I mean, that's decision theory to do with utility and so forth. And it might be that for faces, you want to err on the side of high recall and rather than high precision.
Yeah.
So maybe the measure that you're using, average precision, may not be the right thing to do, right? Because average precision is a way to find one number for this curve, but I suspect what we want is that if this is like this predatory animal threat thing, then you want to have err on the side of high recall.
Right. So thanks. I certainly agree that humans, I mean, from what I get from skimming the literature, humans seem to be tuned at that end of the scale, that they're ready to see anything as a face. And then whether that explains everything, I'm not sure it explains everything.
No, it may not explain everything, but at least you have to take that into account and see how much is accounted for just by that.
Yeah. Okay.
I have sort of a follow-up question. Like, I'm wondering, are you aware of anything in the literature for doing this, say with I don't know, sound and maybe a phoneme, like a O sound or something like that, like trying to search over a database of audio files and try to find language similar sounds.
That's great. Josh, do you have comments on that?
Yeah, I've thought about this, and I'm not aware of good examples of this. There's huge priming effects, right, where you can have very degraded speech, and if you sort of know what you're supposed to hear, profoundly changes the experience. It's not quite.
I wonder whether an equivalent might be mama, which parents hear everywhere, despite the fact that there isn't a lot of evidence that the baby is actually saying mama.
So I was just going to ask, I guess one of the most remarkable aspects of pareidolia is that in addition to just the classification of seeing it as a face, you also recognize an expression. And oftentimes the detailed aspects goes into that. And also, at the same time you recognize it as being a face with all that expression, you're still aware that it's a loaf of bread or a mop or whatever. It's not like the recognition of the face replaces that thing. It's almost as though it's kind of at a different level of recognition on top of that. And I don't know, how do you see it?
Yeah, I think that's right. And some of the fMRI, or I don't remember the modalities used, but some of the physiology literature that they describe talk about how the representation originally starts out just being a pure face thing and then migrates to being really a combination of the two. Yes.
Yeah, so this is a great talk. I think there's one question you asked here: why do humans see pareidolic faces? I mean, isn't the answer just as simple as, I think someone of you said it before, that there was so much evolutionary pressure, it paid very well to be able to see faces, in the Serengeti, and so the system would rather false alarm and then say, oh, that was an error, than not, right? And like, isn't that just maybe like the simple explanation for what's going on?
Yeah, and I guess the one thing is with our computational model, I have to double check with Mark, but I thought that they tried just lowering the threshold dramatically, and it didn't really give the effects that we were looking for here. And we had to actually train on these, different configurations of a face to get the pareidolia that we're looking for. So with our algorithms anyway, I believe it's not just adjusting the threshold, it's got to be that plus allowing more deformation than the algorithm wants.
Okay, so Justine was disagreeing with you. I will disagree with Justine, but to disagree with you more so. And, okay, so let's take the hypothesis of we want to detect faces of animals in the wild. That has an evolutionary advantage. But then the prediction, so then I think it's testable, because the prediction would be that you get lots of pareidolia for things that are dangerous, like snakes and spiders that people have phobias for. But I'm not aware that we have an enhanced pareidolia for spider-like things and for snake-like things or tiger-like things more than for cows or anything else.
Great, I love it. Yeah, you'd also expect greater pareidolia for a cliff edge, or just all sorts of things that would.
Exactly. And so that put some caution on that hypothesis.
Yes, sorry.
Yeah, I have a related question. So your, TC, the frog plot, right? It showed that the pareidolic faces, they cluster together, at a part of the kind of the Tisney space that contain all the animal and human faces. Have you looked at which kinds of animal faces were close to the pareidolic faces? Like I had the same question, right?
Yeah.
You proposed this theory of predators, making you more sensitive. Like could it be, whatever, snakes or, more non-mammalian faces?
Oh, that's great. That's great. Thank you. Yeah, that was fine.
Just for the experiment, I might have missed it, but you asked people to detect faces in the noise. So might it have happened that they were just tuned to really focus on parts of the noise that resemble the face for them, and then say, okay, I saw a face. But if we wouldn't prompt them to look for faces, would they have ever seen a face in these noise images?
Right. I don't know. And I guess the one control of that is we asked them that same question for all these different flavors, if you will, of noise. And so they did tell us that for the ones off the pareidolic peak, they did report that, no, we didn't see a face there. I saw it here. Anyway, so we asked them, do you see any faces? And they would say no. So they weren't only telling us, yes, they saw a face. So I guess the different question is, tell us what you see here and how many of them you see or something. That's great, thanks. Yes.
Thanks. So the face cell in the brain that fires specifically for the configuration of two dots and a sort of something underneath. Could this just be a legacy of that? So like, I think from the infancy work, the face cells will fire some very impoverished stimuli of just two dots and a dot beneath. And if you invert it, like a dot underneath and a dot on the top and two dots beneath, it doesn't fire. So it's a very simple trigger for that cell to fire. And like it's been said, like it's a significant enough stimulus that we need in innate mechanism to pick out face from as early as possible. So could pareidolia just be a sort of like an appendix, like a legacy of that cell firing? We know we've got a better idea of what a face is now as an adult, but that cell is still firing when you get that simple configuration.
Yeah, maybe. And I guess I would argue that you wouldn't see pareidolia for anything other than faces, though.
Yes.
And I think, anyway, so, I mean, there are examples of non-face pareidolia, but anyway, that's a good point. So basically, we have to start out with a really primitive face detector, and we just keep it around.
Viola Jones.
Yeah, Viola Jones.
So what are examples of known face pareidolia?
Well, that one I showed, the sleeping elephant mountain.
Oh, I see.
I don't know.
So is it, are they elephant, are they animals? Is there some, like, are they, like, is it always living things or there's pareidolia for non-living?
I don't know.
By the way, one thing in the camouflage literature, I mean, I've read some of the literature on animal camouflage, and the thing which they point out is that the hardest thing to hide is the face. So, because the rest of the body of the animal, it's a texture, and you can be in a setting where your texture is similar to that of the background, but faces are hard to hide. So, essentially, building a good face detector is a good way to detect generically a large number of animals.
Yeah.
So that's in support of your thing.
Maybe what we can do, I want to open the discussion up to all the speakers and all the topics. We can ask more questions about pareidolia. I think there's enough to fill the whole time. But can I ask now for the other speakers to come up to the stage? We'll have some open discussion where you'll get I can pick on you, but actually it's a discussion for everyone. We want these discussions to be broad and the whole audience is involved. So let me get a few chairs and then